All right, your final test, written test number 2, this Thursday. Okay, I'm still making the test question here, so I may not be able to provide you guys like example questions. But what I'll do instead is like this, also to help you. On Wednesday, so I'm going to turn maybe the final 20 minutes of the class, or maybe 30. We'll see how that goes. We just got to finish something today about the LTL. Maybe on Wednesday, I'll spend at least 20 minutes with you guys. You can see if you got any question. It's more like a Q&A session. And then, since I'm not going to be able to provide you with an example question there, I'll give you guys more explicit hints about how you may want to focus before the test. Hopefully that work equally, right? That's what I would do. Right? Just make sure you don't miss the class on Wednesday, right? Well, it's going to be recorded anyway, but that's something I would do. But I would say for now, you already know the coverage for your written test number 2. You want to focus more on the example that we discussed in the class, and also to review the formulation about different operators. I think that will definitely help, okay? And for your, also I know that I still owe you guys the in-class exercises. I'm still working on that, hopefully either tonight or tomorrow morning. It's still on my mind. It's not my priority. I'll make sure I get it done. Okay. And your lab number 4, the final lab, I will release it maybe after your written test. It's a fun lab. It's going to be, again, a different thing for you to work on, to use a model checker. I'll also highlight it a little bit maybe next Monday, okay, about what the lab number 4 is about. And for this week, my office hour only 3 to 4 p.m. on Wednesday and Thursday. Unfortunately, since I just need to coordinate another course like last time. But if you want to speak to me, Wednesday, 3 p.m., not a problem. I'll give you guys priority if you need to speak to me on Wednesday. All right, if you want to still reach out to Andy about any lab related question, you can feel free. He's ready to take your questions. All right, anything you want me to clarify at this moment? Alrighty, let's recap very quickly, okay? And then we'll try to finish the last bit, or most of it, okay? So last time was a pretty brief lecture, but I think it was still very useful. So we actually spoke about the final pattern, about infinitely often over here. So we already talked about the formulation in the lecture before. We just talked about what will be the corresponding proof and disproving strategy. I think this is really something you guys want to get used to. If I give you a slightly different combination of the operator, for example, in the exam or the written test, you have to know what's the corresponding proving and disproving strategy, right? That's something you want to really get used to. But the principle is really the same about how you prove or disapprove universal versus existential quantification, right? It's really the same principle. All right, and then we did some exercises on GF and over here. And of course, this is an exercise I'm still owing to you. I'll make sure I get it done, right? Tomorrow morning, the latest, you'll get the solution to these exercises. All right, and then we spoke about 2 exercises just to choose the right logical relation between pairs of a temporal operator. So you can definitely review the details. For example, here, G global property is a stronger property than infinitely often, right? We spoke about how exactly you understand it, and just pay attention to this. Whenever you're trying to draw, let's say, this is strictly stronger than this one here, you want to know what's really that witness example that can satisfy this, but not this, right? Visually, there's got to be some member that's in the bigger set, but it's not in the smaller set, right? That's what you guys learned back in the 1090. 1019 or 1090. Right? The second exercise we did is about FG versus GF. I would say this one is a little bit trickier to really see which one will be stronger. But again, so this will be the final answer over here. But you also need to know how there is a special case that can satisfy infinitely often, but it cannot satisfy eventually global true. All right? So that's really something you want to review from last time. All right, so that's about what we discussed last time. Any questions? All right, let's now talk about the final 2 things of the LTL. We want to talk about 3 more operators. And so they will somehow be defined in a complicated way, but given the formulation we have gone through, they may not be too bad. So today, my main goal is to give you, number 1, the formal definition, and then you guys can think about how to prove or disprove them for the exam. They are not covering the written test, so you definitely got time to digest them. They might seem pretty confusing at first. They are inherently more complicated than the operator before. For example, you can see the F, G, and next operator. we call them a unary operator. After them, you only got a single formula phi. But the coming three operator, we're going to finish off, they are binary operators, meaning that for each one of them, you got to consider two properties. Right? So you're going to see exactly how to distinguish between these three. So today, I want to focus more on formulation, just to give you guys really the formal definition, help you understand them. They are already on the slides, which I'm going to go over very slowly with you. Okay, so the until operator, okay, and also the weak until operator, like a weaker version. Okay, and also we got a release operator. So I'm going to go over the formulation with you one by one, and then we'll see how much time that's left. And I can either do some exercises on model satisfaction, or I can maybe just show you how you can use these operators to formulate some English sentences. We can do either one. Okay, we'll see how the time goes. I may have to leave one of them maybe for Wednesday quickly before we move on to the program verification topic. But we'll see. And let's now talk about these three. All right, so the first one is called until operator. Okay, so the way to write it, you can either write U over here, we can write U over here, doesn't matter, as long as we can recognize it. It's called until operator. Intuitively, you might be thinking, phi 1 must be true until phi 2 is true. But this intuition is too ambiguous. We want to make it very formal, precise about exactly what we really mean by phi 1 should be true until phi 2 is true. Okay? And we'll kind of visit this informal description in just one moment, but let's now see the formulation. Okay, let's see that. What does it really mean? When I say phi 1 until phi 2, phi 1 until phi 2. So let's define this using a path satisfaction. Okay, so we say that pi is a path. It will satisfy phi 1 until phi 2, right? So think about this is an LTL formula. And this is just another one. Okay? They don't need to be related. They're just independent formulas. And we'll say if and only if. Okay? In some way, we have to somehow nest existential and universal. We're going to say something about there is some future point where something is true. From that future point, something must be globally true from then on. That's something we're going to say in the formulation. But let's see exactly, and then we'll visualize it. So what we say is, over here, we start with some existential quantification. We say that there exists I should be a valid index, right? Should be larger than or equal to 1, cannot be 0. And right here, okay, let me just make it a little bit smaller, right here. Once we find that future point, okay, so let's say I here. So think about I is right here, right? Once we find that future point, so there's two things we need to be sure. Thing number one, we want to say something until phi 2. Phi 2 must be true at this future point. Okay, so we'll say pi I satisfies phi 2. If you only look at this part alone, it's pretty straightforward. We just say at some future point, the second formula phi 2 must be true. Okay, and to complete the meaning of the until, we say that before this future point, we require all these states up to, but not including. We don't need to be including this particular state. All of these must satisfy phi 1. Okay, let's now write it down. So we're going to say something like, use another dummy variable for every j, 1 less than or equal to j, less than or equal to I minus 1. I explain what I minus 1 really means in just one moment. That implies pi j satisfy phi 1. So that's the full definition for until. All right, let's now do some, okay, let's just talk about this one here first. So here you can see j less than or equal to I minus 1. What that means is, for this particular future point, where phi 2 is actually true, we're talking about all the previous point. 1, 2, all the way to I minus 1. For all these previous points, phi 1 must be true. So what we get is, you basically got phi 1, all the way to phi 1. Whether or not phi 1 is also true in SI, we don't insist on that. It's okay, either way. Okay? Whether phi 1 is true here or not does not matter. It's not going to suddenly make the until true or false, right? It's not part of the definition. Does not matter. One of the operator we're going to talk about is going to insist that phi 1 is also true in SI. That's something we'll see. I'll highlight it to you. Okay. And let me just do a little bit more coloring here. So think about this is the first formula, phi 1. So we say phi 1, right? And then we also got the second formula here, phi 2. So phi 2 must be satisfied at some future point right here, right? If you like. That's until. All right. Any question? Formulation. Okay. All right. If you're okay with it. And then I'm going to put two questions over here that we can think about. Okay. I'm going to put two scenarios for you. Okay. Question 1, question 2. Is it okay that globally true phi 1, but is globally true not phi 2? All right, so think about this question here. I'll pause it a moment. Let's say this is a particular path you're given. In this particular path, phi 1 is always true. However, it is always the case that phi 2 is never true. Now, according to this particular pi, is it going to make the until true or false? That's my question.
It's going to be true.
Is it going to be true?
Yeah, because let's say at this state SI, it doesn't matter like at SI or like after SI, phi 1 is globally true on but then phi 2 has to be true from SI.
Sure. Thank you. Adrian, you got any other thoughts or you agree?
I think for regular until it's going to be false because regular until requires that there's some future state that satisfies phi 2.
Okay, maybe there's something kind of missing over here. So guys, okay, for this, you're kind of right. So for this question here, you can see what you want to focus on is here. This one here. This one tells you for this particular path, phi 2 is never established. Never, ever. There's not a future point. This one tells you, alternatively, it is not the case that at some point in the future that phi 2 is going to be true. And that's exactly what this condition requires. Okay? This one here really requires that at some point in the future, phi 2 is actually true. But since this is not the case for this particular path, so no, this is not okay. No, it's not okay. Okay, recap. What I'm asking here is to check our formal definition understanding. We talk about the formal definition for until, and then I'm giving you one path where the condition here is never satisfied, never ever. In that way, it's going to violate the future point property for the until. So that's why it's not going to be okay for until. Until is going to be false. To be more precise over here, that means phi 1 until phi 2 is going to be false.
Professor,
Yeah.
I have a question. We've been doing the example of the three states, S0, S1, and S2. Let's say our path is from S0, S2, and then S2 has to continue. So the state points to itself. So phi 2, let's say that is related to S2, like that's where it gets satisfied.
Mhm.
So since it's pointing to itself, it's gonna be
Exactly,
true.
exactly. So what you're saying is more specific to the example, which we'll do a little bit later, because now we don't really have the graph reference just yet. I think it could be a little bit confusing to talk about it. We'll get there as we get there. Yeah. Don't worry, we're definitely going to revisit that diagram we're familiar with and see how these operators can be understood. Yeah, John, go ahead.
There can be multiple times where phi 2 is like true on this path, right?
Phi 1, you meant?
Well, even phi 2, like, right? Like if there's a
Oh, yeah, exactly. Yeah, exactly. So, okay, that's a good question here. For your particular path, it is right. Phi 2, there might be more than one future point. We say at least one. But for that particular future point, it must be that all the previous states, like up to I minus 1, must satisfy phi 1. That's the thing. There might be a certain future point. Yes, you may have this one being true, but maybe all the previous point, they don't necessarily satisfy phi 1 for every one of them. You want to find that future point first. If there's such a future point, you prove for until. Good. All right, question number 2. Okay, for question number 2, is it okay that, let's say we got globally true, phi 1, and future phi 2. Imagine we have a path where at some point, guarantee, we actually got phi 2. And then we say globally, phi 1 is always true. Is this going to satisfy until?
Yeah,
It is going to, right?
yeah,
Okay.
it's going to be true.
Uh-huh.
Because as per the statement, it says there will be a phi 2 which is true at a certain point.
Yeah,
and
for example here,
phi
it will
1 is
satisfy
already
this.
globally true. That means both the conditions satisfy.
Yeah, exactly. Okay, why this one is so interesting, I'll draw that to you. This is more like a case you might be thinking, am I doing a little bit too much for until? It's okay, it's okay to overdo, okay? So this one is going to be true. Meaning that if you try phi 1 until phi 2 is going to give you true. Okay, for this one specifically, let's visualize it. What we have is something like this. Let's say this is our infinite path. We say that, first of all, we have some future point where we got phi 2. Let's say this is a future point. We got phi 2. We also get this global property here, say G phi 1. That means phi 1 is basically true all the way through. As far as until formulation is concerned, this part here, we definitely got it for phi 2. And how about this part over here? We're saying that everything from 1 until I minus 1, we should really get phi 1 satisfied. Indeed, we have it, right? Because everything here is actually satisfying phi 1, right? So this path here is actually more than necessary, more than sufficient for until to be true, all right? Okay, so these two are just meant to give you a little bit more insights into the operator. John?
Can the state be the same where like phi 2 is satisfied? Like if it's the first state where phi 2 is satisfied?
Okay, good. So if, yeah, that's good. There will be some special case. I like that question here. I think that deserves a separate page. What John is talking about is some special case. Okay, I'm going to make it a little bit smaller. Okay, let's now review this until operator. Let's say we got this. This is our path. Okay, let's say this is state number 1. And let's say that one there already satisfied phi 2. That one is already there. Okay, now the question is, since we already satisfied phi 2, there's a future point right here. Are we going to satisfy this one as well automatically? That's the question. If I ask you this on the exam, how would you justify it, right? John, what's your thought? Do you think the orange formula there is going to be satisfied automatically? Guys, I'll give you hints. Think about the universal quantification where the range is empty. Does that hint kind of make sense to you? I'll go a little bit further. For this particular one here, okay, let me just copy this formulation here. Right here. All right. By the way, phi 2 is really the green one over here, right? So phi 2 here, we already satisfied this. That one is not a problem. All right. So we're talking about I here is just equal to 1. So S1 is a very first state, so that means I here is just 1. That one already satisfies phi 2. So why don't we substitute the occurrence of I just by 1? So what we do is, why don't we look at just this part over here? If we satisfy I just by 1, we're going to get 1 less than or equal to j less than or equal to 0. Now we got a false range for universal quantification. Remember one of the property? If you got false range, false implies anything. It will be true, trivially. Okay? It's a very, very important base case. I'm so glad actually John mentioned that, so I can talk about it. Okay, this one here can just be boiled down into, you got for every j, and then you got false. Implies pi j satisfy phi 1. Okay, and we know that this one here, trivially, by the 0 of implication, right? This one here would just be true. John, make sense to you? Okay, I'm glad. Maybe, I think, I don't really remember exactly, maybe one of the exam question in the previous year was somehow based on this insight. So you can definitely make a note on this. I don't mind if you put it on your data sheets to remind yourself. If you learn the stuff, I'll be happy. Okay? Very subtle here, but it's important, okay, about a logical property. Okay. Okay, think about it, and then if you want me to clarify that further, we can also do that. Okay. Okay, so that's about the until operator, and we got 2 questions here. I'm going to introduce the second operator in the next page, and then I'm going to ask the same 2 questions again and see if the answer might change. So that one can also kind of illustrate the difference between these 2 operators. Okay, I think that'll be the way to kind of go. All right. Okay, second one. The second one has a funny name. It's called weak until. Okay, first of all, let's now write down the name. Weak until. Weak in the very logical sense. That means there will be more paths satisfying the weak until operator than the normal until operator. Okay, so let's now visualize this right away. Think about the one we just talked about was the until operator. If you think about, I got phi 1 until phi 2. This one is the normal version we just introduced. That one is strictly stronger, which means there will be fewer paths that's going to satisfy this until operator. Okay, and the one we're going to do it now is the weak version. That one there is going to be phi 1 weak until phi 2. As soon as we visualize this way, that tells us there's got to be some path that will satisfy the weak until, but it will not satisfy the stronger version. Right? That will be something you want to keep in mind. There's got to be some weakness over here that is going to satisfy the purple one, but not the blue one. So that one is going to satisfy the phi 1 weak until weak version, but it's not going to satisfy the normal version that is stronger. And you will see that once I go over the formulation with you. It's actually quite obvious, like which kind of like a more tolerance we're adding to this weaker version. We'll see that. All right. Okay, keep that diagram in mind. I think it's going to help a lot. All right, let's now go over a formal definition for weak until. Okay. So we got, let's say, phi 1 weak until phi 2, if and only if. We're going to start with if you're able to satisfy the normal until weak until is true. Okay, we're going to reuse the definition. So number one, we're going to say if phi 1 until phi 2 is actually true, that'll be okay. Okay, so we're basically saying in order to make this set right here, we definitely want to include all those that will satisfy the normal until plus something else. Okay, what about that something else? That's something we're going to see. That'll be the new information you have to watch out for. So I'm going to say, since we can allow other property to be satisfied in order to make the weak until version satisfy, so I'm going to say disjunction. Right? Allow a different possibility. And this possibility here will be over here. For every k larger than or equal to 1, pi to the k satisfies phi 1. Doesn't that look like something we have learned before? Which operator?
That is global phi 1.
Exactly, right? Yeah, sometimes the standard definition will just write it out for weak until. So I'm just telling you, it's really equivalent, right? So this part over here, as Adrian correctly pointed out, that one there really is about globally true phi 1. So the way to think about a weak until is like this. Whenever, if I ask you to really check for weak until, right, you can first of all try to check it as if I'm asking you about the stronger version. If that one is already satisfied, good, you don't need to check any further because the OR would have been satisfied already. Or if you find it's easier for you to simply see if the global phi 1 is actually true. If that one is also very easy for you to see. If you see that's true, also you're done because you also got one of the disjunct satisfied. So overall, it will also be true for weak until. All right. Let's now visualize these two cases. All right. Let's say case number 1, case number 2. Let's say this guy here is case number 1. Okay. Case number 1. Right. I'm going to put case number 1 right here. That one just the until that we just saw earlier, right? That one there tells you there exists certain I where phi 2 is actually true. And then as long as all the previous states, which doesn't need to include Si, you may or may not, but it doesn't need to. S1, S2, all the way to Si minus 1, they will satisfy the second property, which is phi 1. Okay. So think about case number 1 is really about phi 1 until phi 2, right? So this one just consistent with what we said a little bit earlier. And the second possibility, which is case number 2. Okay, let me say this is case number 2, right? So case number 2, just say phi 1 is always true. So phi 2 never get a chance. Okay. Oh, let me take it back. Okay, let me visualize first, and then I'll say it more correctly. Okay. So here we're saying that phi 1 is simply true. So phi 1 and phi 1, phi 1 and phi 1. And this one here is simply globally true phi 1. And it is important to actually know the following. We just say that globally true phi 1. Whether or not phi 2 might be eventually true, we simply don't care. It may or may not be. It's not necessary for us to know. All right? Whether or not globally, eventually, phi 2 does not matter. All right, guys, any question so far? All right, so what I would suggest is we're going to revisit the two questions that we asked earlier about the until operator. Okay, let's revisit them. Okay, and then we'll see. Okay, so let me make some space right here. And then we're going to go over that particular question. Oh, sorry, let me do it a little bit better. There we go. Okay, one more time. Okay, good. Perfect. So for this one here, I'm just making a little bit smaller. Okay, right here. So maybe I can put this one maybe right here. And then I'll put a diagram right here. There we go. Okay. Just don't forget, this one here goes with this explanation, right? All right, let's now revisit the two questions over here about weak until. Question 1. Is it okay that we got globally true phi 1, but phi 2 is never established? Let me remind you, the same question over here, when we asked about it for the normal version, we said no. Because the normal version of until does ask phi 2 to be eventually true, right? There's got to exist certain point. But now for the same property of this particular path, is it okay for the weak until? Obviously, right? It's really because of this new condition we're adding to the definition, really here, okay, by definition, all right? All right, so this will be okay. This is really the key. Okay, so that means the phi 1, weak until phi 2 will just give you true. Not a problem. So this one clearly highlights the difference between the until and weak until, right? Really important. All right, let's now do another one. The second question here, is it okay that we got globally true phi 1 and eventually phi 2? Is this okay? Yeah, obviously, right? This one here and this one here definitely match. All right. Also okay. Yeah, really use these two questions for you to check, about the formal definition for the two operators. Okay. John.
Like future theta phi 1, future phi 2, then until
Future phi 1 and future phi 2?
yes, that won't both be either. Right?
Yeah, if you say, okay, that's a problem here. So let's say here, right? The question was, if you only got future phi 1 and also future phi 2, okay? This part here is good because you know this certain point. But the problem is future phi 1 doesn't really say anything about the subsequent, like a previous state satisfying phi 1, so it's not enough for you to conclude the until will be satisfied.
It can be and it can be not.
It cannot be.
It cannot be not.
It is not sufficient. It is not sufficient. Okay.
There's a case where like if it's S1, if it's
I'm just saying in general, okay, let's say this. Okay, I'll make it clear. Okay. Given a path, where we say future phi 1 and future phi 2. Okay? So what we are saying here, if you visualize it, we'll just say at some future point, phi 1 is true. At some future point, phi 2 is true. If I can give you a witness that's going to contradict the definition for until, then we're going to say this path cannot be sufficient in general, right? Okay, let's say this. So now if I got, let's say this is future point for phi 2, which is good for this guy here, right? Let's say this is SI. That one's good. But the problem is the formal definition for until asks for all the previous states until I minus 1 should be true for phi 1. But the future phi 1 is not logically sufficient for that, right? Okay. So this will be from S1 all the way to Si minus 1. And so this one here, not necessarily globally true phi 1 from S1 to Si minus 1, given only this one here. It's another good question. I think just keep asking this. We can keep clarifying, right? All right. Yeah, Daniel.
Is there a reason why for until you wrote it as conjunction, but then for week until you wrote it as conditional?
No, actually, good question here. The conjunction you're talking about for until has nothing to do with the disjunction there. Okay, so let's say until. The conjunction here tells you that not only that you have to make sure the phi 2 must be established at some point, but also all the previous state must satisfy phi 1. That's a conjunction, right? This conjunction here is somehow contained in the weak until. Because remember, if you look at the definition for weak until, this one here is the whole definition for until, which includes the conjunction. This disjunction over here simply tells you if you didn't really satisfy until, that's okay. I'm defining a weaker version. I'll give you another scenario that's going to also satisfy the weak until. This is a scenario, right? So the recap would be this one here does include the conjunction that's actually used to define the until. More than that, we also got a disjunction to allow another possibility. That's why it's the weaker version. Good. Good question. All right. All right, if you're good. Okay. So I would suggest that we're going to maybe save these model and path exercises, just only 2 pages. These 2, we can do that on Wednesday in the beginning, so you guys can get a little bit more familiar with the formal definition before Wednesday. Take a look, spend a few minutes, and then we can do the exercises together, okay? So why don't we try to take a break now by taking attendance, and then I'll just finish the definition for release, and then we'll do some fun exercises, okay? And then that's it for today. All right, so before the break, we spoke about the definition for until and the weak version, okay? Now the final one is called release operator, which might seem very close to one of them, but I'm gonna highlight to you, they are not exactly the same. There's some subtle difference, which I'm gonna give you as some exercise for you to contrast them, but as long as you pay closer attention about the 2 operators, you should really see that they are not exactly the same, okay? Let's now talk about it. It's called a release operator. Release. Okay, it's called a release operator. Intuitively, you can think about the establishment of phi 1 is going to release the holding for phi 2. That's why it's called release. As soon as phi 1 is true, it can somehow release that phi 2 must be true. Somehow. Okay? But of course, might be a little bit easier if you see the formal definition. Okay? Let's see that. So formal definition goes like that. So pi, some path, satisfies phi 1, releases phi 2. If and only if, right? The definition is going to be somehow very similar to the weak until, somehow. But I'm going to let you kind of contrast them in a moment, okay? Just before I give you the formal definition, right? So you really want to do some extra reflection on your own. Okay, I'm going to suggest over here, okay? Contrast. Okay, you may want to think about, what if I got pi satisfies, and now notice one thing here that's important. So here you say phi 1 releases phi 2. But when you want to look at the corresponding version for weak until, you got to swap the order. Right? You'll see exactly why once you see the formal definition. Okay? So you're going to say phi 2 until phi 1. Okay? So that's something phi 1 right here. And also phi 2 right here. All right? So that contrast exercise, please do it. All right? If you look at the formal definition closely, it's not difficult. But you want to have that kind of understanding before writing the exam. Okay? And then let's now take a look at the formal definition. Let's start with something simple. Okay? It's going to be a disjunction, kind of similar to like a weak until. So disjunction here, and then I'm going to put something you have already seen before the break. For every k, k larger than or equal to 1, pi k satisfies phi 2. Right? So this one here really is about globally true phi 2. Remember what I said? Oh, sorry.
You said it's the opposite of weak until.
No, it's not the opposite, just a contrast. When I say contrast, I mean try to look at phi 1 releases phi 2 versus phi 2 until phi 1. Look at these two. Compare the formal definition to see how they are different and how they are similar. That's my point, yeah. They are not the opposite, by the way, not really. Yeah, okay, good. All right. All right, so this one here is kind of easy to visualize. We're just saying globally phi 2. Because we said intuitively, phi 1, once it is true, is going to release the pressure about phi 2 being true. It is okay if phi 2 is globally always true. That will be acceptable. So that in that case, it doesn't need to be released, really. Okay. So this one here would just be basically globally true. Globally true. So that one there would be phi 2, phi 2, phi 2, phi 2, phi 2. And this is like a case number 2, okay? Case number 2. So you can think about case number 2 here is globally true, phi 2. So there is no need, there's no way to release it. It's just always true. All right. All right, that's one. And what about the other possibility? That one going to require a little bit more complicated definition, but it's not too bad. We have seen that pattern already for until. That one there is going to be something like, there exists I larger than or equal to 1 is a valid path index. And this part over here is going to contain two parts, okay? Pi I satisfies phi 1. Let's visualize this part right away. This one is saying there should be certain future point at index I that satisfy phi 1. Let's now visualize that. So you can think about this is at index I. So that one there already satisfy phi 1. Okay. And then we're going to say that right here, the second part, for every j less than or equal to I, pi j satisfy phi 2. Guys, just by looking at this particular universal over here, can you kind of recall, is this similar to how we defined the until or a little bit different? What we're saying here is, we're asking, this is a future point where phi 1 is actually established, right? And we are saying that all the previous states from 1 until I must also satisfy phi 2. That pattern kind of seems familiar from us, right? From previous one, okay? I'm going to tell you exactly, okay? First of all, let's now try to make it clear. So we say that all the way, and then don't forget, it tells you also for SI. That one there must also satisfy that. So we got phi 2, also phi 2, also phi 2. That means at this particular future point where phi 1 is actually satisfied, phi 2 must be satisfied at the same time. Okay, that's a critical point you want to remember. Okay, so that'll be case number 2. Beg your pardon, case number 1, of course. Case number 1, okay, but case number 1, not exactly. Phi 2 until phi 1. And exactly why, you want to look at the formal definition yourself to actually find out. Okay, that's a simple exercise you can do. All right, any question about the formal definition here? We're good? Okay, now take some time to digest, especially for release. Think about release, it's kind of similar to the weak until and until, similar, but there's some boundary case that's not exactly the same. You want to be careful. All right? All right, so what I want to do now is let's now do a quick visual summary about these three operators. So at least intuitively, you can understand how they work. And then for today, I just want to do a little bit of formulating English sentences using temporal operator. I think some of them are quite fun to actually look at. Okay, why don't we do a visual summary quickly, and then we'll do that exercise. And then on Wednesday, to start with, I'm going to talk about some path and model satisfaction exercises on these three operators to finish off the topic. And then we can go to the next one. Okay, let's do a summary. Okay, just visual summary basically. So we got the until, weak until, and release. So we got the until, we got the weak until, and also we got the release operators, these three. Let's start with the until operator. Okay, so that one there, we say phi 1 until phi 2. Okay, let's start with that one. That one there, if you consider some infinite path, pi, we say that there's got to be some future point at index I that will satisfy phi 2. Okay, so we can color phi 2 right here at some point in the future. But we don't insist we don't insist phi 1 to be also satisfied at index I. We don't insist that. It can be I minus 1. So what we say is, for all the previous one, starting from 1, 2, 3, all the way to I minus 1. Phi 1, phi 1, phi 1, and phi 1. Okay. And you can think about we got phi 1 here. Again, whether or not phi 1 is also true at index I, we don't care. It's not relevant. Just not part of the definition. If it is true or it is false, it's not going to impact the result. That's until. What about weak until? So we got weak until. Right, so that one there is going to number 1. If you already satisfied until, you're good. Okay, I'm just going to copy that, right? So this one here is just the same. That one is one of the possibilities. Another possibility for weak until is we're adding more, we're being a little bit more accommodating. So we can say disjunction, or if I got just this, and phi 1 can just be true always. Phi 2 just, we don't care. If phi 1 can be always true. Okay, so this one here is going to be 1, 2, 3, all the way to infinity, right? Phi 1, phi 1, phi 1, phi 1, etc. Okay, that'll be fun too. In the second case, we simply don't care if phi 2 is ever going to be true. It's not relevant. As long as phi 1 can be globally true for all the states, we are fine. All right, so that's until and weak until. Yeah, what about release? And for the release operator, you can look at that maybe somehow together with the weak until. So for the release operator, you can say phi 1 releases phi 2. Oh, by the way, for weak until, I should really say phi 1 weak until phi 2. All right. Oh, sorry. Right here, and then right here, right? For release operator, the case is very similar is, right here, one of the possibility is, if this particular operator, if this particular property is going to be satisfied throughout. Think about the phi 2 over here is like the phi 1 over here, right? It can be opposite, okay? So I think coloring might help a bit when you study, okay? So you can say one of the possibility that we spoke about was if you got globally true, phi 2. Okay, phi 2, phi 2, phi 2. Globally true. Okay, that one's very similar. Okay, but the other case is almost like weak until, but I got to be very careful about the boundary case. Okay, that one there basically is like this, and then we say at some future point, phi 1 must be true at some future point. Index I, phi 1 must be true. Okay, at some future point. But now we're saying that for all the previous point, including at that particular future point, phi 2 must be true, right? Rather than I minus 1 only. Okay. So for that one, it's going to be 1, 2, 3, all the way to I minus 1, right? So what we have is we're going to get phi 1, phi 2, oh, sorry, phi 1 only, sorry. I was counting something nonsense. Phi 1, of course, phi 2. Phi 2, phi 2, phi 2, and also at the same state, also phi 2. Okay. So the most important part for you to see is over here. Okay, let me highlight. For released, pay attention to this boundary case, right? Where in that future point, both phi 1 and phi 2 must be true, but in the case of the weak until, they don't need to be. Could be, but don't need to be. Okay. So I would suggest we spend a little bit of time formulating English sentences using the temporal operators. Yeah, before that, Adrian.
So for A release B, can we say that A release B is equal to B weak until A and B?
Let me discuss that maybe next time when we start with. I think just for your fellow student, get a little bit more used to the formal definition. I'll speak about that. Sounds promising. Okay. All right, so let's now talk about some formulation problem. Okay, you can also, I'm going to talk about these two exercises on Wednesday to begin with, but you guys can also give it a try. Okay. Okay, this one's interesting. Okay, let's spend some time on this one here. First of all, talk about a natural language. Let's say that's what you're given. I had smoked until I was 22. If I say that, okay, you might be thinking, can we use an until operator? It will make sense, doesn't it? Okay. Now, the question is, can we actually say something like, I'm basically saying, using an until operator, and say, I smoke until I was 22. So this is another kind of exercise we want you to get used to. Now that we learned about the math, we are using that to formulate some real-life constraint. Now, is the until operator really formulate what we really meant to say over here? That's a question. Most likely not, right? Otherwise, what's the point of discussing this, right? Now, I want to know, do you know exactly why the temporal until operator is not going to formulate what we're just saying here?
So the temporal thing says that you smoked before you were 22, but on or after when you were 22, it doesn't say anything about whether or not you smoked. The natural language kind of implies you stopped smoking when you smoked.
Aha, that's pretty spot on. Good, okay? Let me write down exactly what you say, and then we'll try to see what the correct formulation might be. Very good. Okay. The until operator only exists smoking up to and not necessarily including 22. On the other hand, if you look at the natural language over here, the until, you will agree, we are really saying at the point that you're 22, you basically stop smoking, right? All right. Let me give you one example here. Okay, let's visualize that. Let's say this is what we have, right? At some point, you can think about this as phi 2. There is a future point when I was 22. Indeed. There's a future point here. In order for the until to be true, it would be okay if I say, for example, I smoke here, I smoke over here, I smoke over here, I smoke over here, I smoke over here, I also smoke over here, and all the way. It's still going to make the logical until true, according to its definition. Agree? So it's not really formulating faithfully what we really meant over here. Okay? This is going to make S until T will be true, but not really what the English sentence is saying. Natural language is meant to say. So what we want to do instead is to say not only that until, but also we want to say as soon as you reach 22, it is globally onwards, you're not smoking anymore. All right, so that's a part that's kind of trickier. So what I'll do is I'll give you the answer, you can think about it. All right, well, any suggestion? We just have to somehow extend this a little bit, especially this part over here. This part here should not be just about I was 22. It should be about after I was 22, I don't smoke anymore. You need some kind of nesting over here. Any idea? Okay, let me start you with. So this will be some fixed version. I smoke. This is okay. I can still keep it. And until operator. But now, the second property here, I got to be more elaborate. Not only that, I'm going to say that I was 22. I mean, write it down first. You can tell me, right? That one there should be there still. And what would be your suggestion?
Could you add like a global operator?
Yeah, you may. What would you want to say with the global operator?
Until I was in after 22, I'm not really sure what to say.
Sorry, say it again.
Basically, I used the global operator to specify that after you're 22, the condition would hold.
Yeah, exactly. Something like that. That's exactly right. Okay, so what you want to say is, okay, so this is good. We keep it, right? At some future point, I was 22. That one's okay. Not only that, and also from that point onwards, global okay, some global operator over here. Okay, I'll sketch the idea. You can see the exact answer also on the slides. I was 22. That's true. I already reached that stage, reached that age. And also, it is not a case that I smoke. So this is the extension I need to add. Okay. Yeah, think about this example here. That one really tells you you cannot just use it until like English until. It does have some logical inefficiency that you actually naturally have, right? Compared with what you really meant to say in the natural language. So the way you study this example here, number one, you should really look at the natural language again to see what it really meant to say. And then compare the original version here with the final version over here to see what the differences are, right? Okay. This might be the trickiest one, right? Others are not as bad. Okay, I also included the definition for until you can also look at. Okay. Yeah.
One question. So like the second part where like in the global, like I
Yeah.
was 22. Is there ever like I know like logically it can be, but like that you're not 22 after you're 22?
I know what we're going to. I thought about it earlier this morning. I noticed that, but I could have maybe tried to rephrase this one a little bit. Maybe I was at least 22, right? Because when I go to 23, I'm still at least 22. When I go to 24, I'm still at least 22. Yeah. So think about this one here saying once I was 22 is true, you're just going to keep say it's what was once true, really. But if you like to be logically making sense, I can say I was at least 22 years old. How about that? Once it is satisfied, I will, of course, it will always be true, right? That would be more precise. Yeah, question? A question somewhere? Yeah.
So the until operator kind of implies that like you smoked at like when you're 1 year old or 2 years old. Is there a way? How would you like change it to restrict it to like a certain time frame? Like we could just change.
Yeah, you may do that. Yeah, actually, yeah, you might be right. Yeah. So maybe that's something you can definitely try to expand this one a little bit. I'm just trying to show you the initial one is actually not good enough. We try to fix something. But this one may still not be perfect. You can think about how you may say, maybe I started smoking when I was 17 until 22. You know, there's a time frame. And after 22, I don't smoke anymore. How would you do that? Right? Okay. All right, let's do a little bit more. Okay. Okay, the second example here. Okay, not as bad. Okay, guys, really, you can relieve for this one here. There's no until needed. Okay, question?
Could you go back to the previous slide?
The previous one?
Yeah. So why do we need I was 22 as a separate statement?
Over here? You want to make sure that this is actually, there exists certain point that this is actually true. And then from that point onwards, these are actually true.
But we're mentioning it in the global operator as well. Right?
Yeah, the problem is if you only say global over here, let me see over here. Let me look into it. Then I'll try to see if there's better explanation for that. But it seems like that one is needed. You gotta make sure that point is actually established already, and then from that point onwards, you want to make sure both are true. I'll respond to you maybe next time. Okay. All right, next one. How about this one here? We're saying that it's not possible to reach a state for the system where you kind of started some request, but you're not ready. So here we can kind of use the starter and ready as like a propositional atom. How do we formulate this using a temporal operator? We don't need until, apparently. Okay, when you say it's impossible, right? It sounds like a global property, right? And so also to reach a state, it sounds like a future property, right? That's kind of the thing you want to notice. Okay. So this one here, impossible to reach. Not the case. At the future, some point, you can have some property. Right? Not sometime in the future. Yeah.
For the blank started and not ready.
Yep, good. And then over here, you got to make sure both are kind of being applied to the future operator. Started and not ready. All right, so that's the answer. Pretty easy. And of course, in the exam, you want to be very kind of clear about, if I give you some natural language over here, you want to identify what's the operator use, right? Or if I say, I give you some natural language description, I give you some candidates formulation. You want to explain or justify to me whether that's appropriate or not. Okay. All right, you can definitely try exercise to formulate this one here using universal existential quantification, right? That one I'll leave as exercise for you. Easy. And you can do a little bit of rewriting if you wish. You can definitely say, when I say not the case, future started and not ready. So there's some property here you can easily prove. I put it here. If I say globally true, phi, it would be double negation. Not the case, as some future I establish phi. For this one here, you can easily try to substitute both sides just by universal or existential quantification definition and prove it. Okay. Another one, if I got future phi, will be equivalent to not the case global and not phi. Okay, you can use it, but you should also know how to justify them. Okay, just apply the definition for the global and future. You will be able to kind of distribute the negation over the quantification. And we spoke about in the math review lecture how you can distribute the negation operator. So now what about this one here? This one here will be equivalent to, over here. So this one would just be global. Okay, and then not the case started and not ready. Okay, and then if you like to apply De Morgan, you can also say global not started or ready. And of course, for this one here, if you like, you can also use the implication definition. You can say started means you're ready. So these are all logically equivalent, right? Just by using the properties that we know about. Okay. Okay. Okay, let's do, we got two more. Okay, what about this one here? This one may be something similar to what you did for lab number 3. Whenever there's a request that's being made, eventually it will be acknowledged. This one does seem to be like a nested quantification. I mean a nested operator, right? Because you can see here, when you talk about whenever, and also eventually, right? Whenever is like a global, and eventually is like a future, all right? But how do we combine them, right? In a way that's gonna formulate it. Any suggestion? John, any clue for this one here? You definitely need some implication, I agree, but at the outer level, would you suggest global or future? Global for the whenever, right? I will start with, let's say global here. Globally, some property. What should I do here? So that one really nicely modified the whenever, right? But now we still got the remaining part. Whenever a request is made, then eventually it should be acknowledged. How do we model that part?
Like requested implies future
Yeah,
growth.
yeah, it's straightforward as that, right? You can say requested over here implies eventually it is acknowledged. Right? This is actually a very, very common pattern, right? It is globally true that whenever something is requested, the antecedent is true, then eventually something is actually true. Right? Notice the nesting over here. And I would highly suggest you try to look at this pattern here and look at its formulation, right? See exactly how the nesting of the universal existential quantification will look like. That's something for you to exercise. Right? Daniel.
Wouldn't it be true though if requested like came after the future state of the knowledge?
This one here? Yeah, yeah, exactly. So, no, we are actually saying this. I see what you mean. What this one is saying is like this. It's globally true for every state requested. Whenever you try to request, let me put it this way. I got it. Let's say state 1, state 2, state 3, state 4, etc. Okay? Number 1, we don't necessarily have to request for every state. Okay? You might try to request on state number 1. You might try to request on state number 3, for example. And for those states you don't really request, it's going to make the antecedent false, which is going to make the implication true. That one we are good. Okay? So for those ones not requested and also not requested, we're okay. We just get false implies anything. What about for those where request is actually true? That means we require at some point in the future relative to that request, it should be acknowledged. Okay? So we are saying that here there should be a future state relative to 1. For example, it could be here where it's actually acknowledged. And also, there's going to be another, let's say for this state here, there's going to be another relative future state. For example, it could be here where it is acknowledged. Right. That's what it is saying. Yeah. All right. Final one. Okay. Take a look at the natural language here. And also we got some atoms there for you to use. Okay, if you like some visualization, I can draw that. Let's say over here, let's say somehow, let's say this is floor number 1, floor number 2, right? Somehow at floor number 2, we're going to press the button to say we want to go to floor number 5. And then we say that once the buttons clicked, then the elevator should really go upwards until we get there. Right? That's kind of visually what the natural language is trying to say. But now how do we formulate it? You might be thinking one thing to start with. Globally true. Let's say I'm not in floor number 2. And then I try to press the button there to say I want to go to floor number 5. And then I'm saying that if this is the case, then the elevator should really keep going up. Would it be okay if I simply say implies globally true, directions up? Is this a valid one? It's a valid LTL, but does that faithfully formulate the natural language there? Daniel, go ahead. Why would it not?
I think because when it reaches the 5th floor, then it can go down.
Yeah, it may go down, but this one here is pretty bad. That means the elevator keeps going up, even if it reaches the tip, of the building, right? So it's not realistic, right? So what we should do is something else, all right? So this is kind of the question you want to really also think about, right? In the exam, I might just give you something alternative. You want to, number one, judge to see whether it's actually appropriate and they justify, right? Okay, this one here is not appropriate. Okay, what you want to really do over here is something like, okay, give me 1 minute and then we are done, okay? So a consequence over here could be directions up. Yes, we need it. Until floor 5. Right, that's what we need. And think about whether or not it is okay if I replace it by weak until. Think about it. All right, so we've done about 4 or 5 exercises over here, so that gives you some idea. So for the exam, you can be asked maybe some natural language, you're given that, and formulate it. Or you might be given some formulation to consider and justify it, or to disprove it, things like that. Right? So that really requires insight into the operator that we have taught you about. All right, thank you, and I'll see you on Wednesday.